Okay, so today we are going to provide an introduction to linear regression. I'm hopeful this is a topic that you all have at least some degree of experience with. You should have seen this in undergrad stat courses or maybe in prior graduate level statistics courses. And so at the end of today's lecture, you should be familiar with the least squares, normal equations. You should be able to estimate a simple linear regression model, and then related to that, you should be able to determine whether or not there's a significant linear relationship, emphasizing the word linear there, between two variables of interest, okay? And so we'll start with just some high-level background on simple linear regression. We'll introduce the method of ordinary least squares, and then we'll go through some examples using a data set we've been working with over the past few weeks with some of the ANOVA exercises. And then as a reminder, we have our mid-semester break on March 3rd, so no class on that date. And so for the remainder of the week, the only deliverable on your end would be the term paper literature review, which is due Friday. And then we'll also see assignment 3 coming out. I should be able to get a sense of what we'll be able to cover between now and next Monday and probably next Wednesday's content. We might have a little bit of that, but that'll primarily be focused on ANOVA and simple linear regression. So with that, we can basically launch into things. So just real quick, let's just get a quick poll of the audience. How many of you have experience in estimating linear regression models? Okay, do any of you not have such experience? And I won't necessarily pick on you necessarily here, but okay, so a little bit of diversity there. And so when we talk about linear regression models, oftentimes in transportation, we're interested in examining research questions or hypotheses that relate to the nature of the relationship between two or more variables of interest. And so in that context, up to this point, we've talked about various types of tests where we evaluate groups. So essentially, we can think of these variables as grouping variables in essence. And we've done that with the rumble strip analyses, with motorcycle fatality data, with travel speed data, a variety of other contexts as well. But oftentimes what we'll find is rather than trying to find differences between groups of variables, we'll have a pair of variables that are essentially continuous in nature. And so we're just, from that perspective, interested in whether or not those variables tend to increase together or decrease together, or if as one increases, the other decreases. And there's various other general types of relationships, but those being the primary ones that we're interested in investigating. And so as an example, over the last few lectures, when we worked through ANOVA, we were ultimately interested in determining whether the depth of milled rumble strips had significant impacts on peak roadside noise levels. And so the way we had investigated that question up to this point was that we took the depths of those rumble strips, we basically aggregated similar depths into groups based upon the ranges at which those rumble strips were milled. And then we tried to assess whether there were differences in terms of the noise levels that were generated at the sites that were classified within each of those groups. Now, a more straightforward way may be to just simply look at the relationship as that depth increases, what happens to the noise level. And we can do that in linear regression and in various other formats as well, but that's going to be a natural extension of what we had started talking about last week. And so within our context, we can basically use regression analysis to build a model which we could use to predict the noise level based upon depth. And we could also control for some of the other relevant factors. And so the content we'll talk about today, we hopefully will get through most, if not all, of simple linear regression. We'll talk about some model diagnostics next week, and then we'll continue to build on this and get into multiple linear regression. And so if we think about everything from a big picture perspective, everything we've done over the first month plus of class has largely laid the framework for what we're going to talk about over the remainder of the course. So the hypothesis testing and ANOVA and some of those other techniques that we've introduced are all going to be critical to our estimation of linear regression models and various other forms of regression models as well. So that's essentially a big picture look at where we're going here. Now, this looks somewhat familiar to the data that you had been working with previously. And so basically what we have here, we have the same 12 sites and we have peak noise levels of interest to us. And so our primary question here is, how are these noise levels impacted by the depth of the rumble strips? And so what you'll see this week as a bit of a difference, and sorry, I've got my web browser open, and so I don't know if you can hear it on your end, but I'm getting email after email after email, and so it just keeps dinging. And so let me just quit my browser real quick. Okay. And so you're all familiar with these noise data that we've been working with up to this point. The one primary difference, well, I guess there's actually two primary differences with the nature in which the data are being presented to you today. First of all, rather than having these rumble strips grouped into 3 general groups based upon their depths, as you'll recall last time, we had established ranges basically every 3/8 of an inch or so up to a maximum, anything of a 1/2 inch or above. But in this case, I'm actually just providing the actual milled rumble strip depths to you here. And so the way these were measured, we basically used the caliper and measured several different rumble strips at each of these sites and then averaged those values. And so as you'll see here, they'll range from roughly 1/4 inch up to nearly 3/4 of an inch. The other information that's presented here, and we're just going to set it aside for today, but we'll circle back to this when we get to multiple linear regression. We also have details as to the pavement characteristics, specifically whether that pavement surface was just hot mix asphalt or if a chip seal had been applied. And we'll talk in subsequent lectures about some of the implications of that on noise levels. But for today, we're largely just focusing on the impacts of depth on peak noise, okay? And so anytime you're starting any type of regression analyses, and this is particularly important with linear regression, but really for virtually any types of regression studies, and more broadly, and we may not have touched on this as much as perhaps we should have up to this point, one of the best things you can always do at the onset is just to plot or graph your data to try to understand what that relationship looks like. And so here we basically see a general plot that illustrates how our peak noise levels increase as a function of our rumble strip depths. And so as you'll see here, it does appear that we have a significant relationship here. We're generally speaking, as those rumble strips get deeper and are milled further, we do see that those noise levels also tend to increase accordingly. And so we'll investigate that a little bit further formally through our linear regression analyses today. But from a big picture level, this would essentially be a first step, because this helps us to very quickly understand whether or not this research question is even worth investigating. Because as compared to this, if we had just seen like a random shotgun blast and a scatter of points all about here, we may have some concerns as to whether it'd be worth proceeding in the course of a regression model, okay? In any case, it appears that it is. And so when we talk about linear regression, I use the term simple linear regression specifically today, and we call it simple in part because in this context, we're basically looking at the relationship between one independent variable, which we'll also refer to that as a predictor variable or a regressor. And we're trying to understand either its relationship or its effect on some dependent variable or response variable of interest. And so our independent variable is X, our dependent variable is Y. And again, I'm kind of yada-yadaing it at this point, but we're ultimately assessing whether or not there's a relationship. That doesn't necessarily mean that there's a causative effect. We'll return to that point later. But at a very high level, we're just trying to understand if those variables tend to change with respect to one another. So as X increases, what tends to happen to Y is our fundamental question of interest. And so if we think about this, the expected value or the mean value of Y for any given level of X is essentially treated as a random variable, okay? So our expected value of y given x is simply going to be a function of x, and you've seen this nomenclature before, hopefully. And so we basically have beta naught, which is an intercept term, and beta 1, which is the slope. And so beta 1 is basically telling us in terms of whatever the units on y are for a 1 unit increase in x, we're going to see this corresponding increase in y, okay? And so that relationship we suspect is going to generally hold across our sample or across the population that that sample is drawn from. And so we can think about this in terms of a model that can be used to determine or estimate or predict the noise level for any given rumble strip depth. And so we operationalize this as a model by basically setting up this equation. So the value of y is equal to that intercept term plus the slope times whatever the corresponding value of x is, plus epsilon. And this is the same, we can think of this in the same manner as we had in our previous discussions of ANOVA. This is basically an error term that's capturing the effects of everything else that's not directly captured or included in that model, in essence, okay? And so we'll talk a little bit more about that subsequently. But basically everything within our context, if we're using rumble strip depth to predict noise levels, that epsilon is capturing all of the other stuff that also influences noise levels. And that would include the pavement type, the baseline noise levels that we had talked about last week, and various other factors as well, okay? And so the way we estimate this regression model is through a method that's referred to as ordinary least squares, okay? And so hopefully this is review for many of you, but let's assume that we have n different pairs or groups of observations. So in each case, in our context, x would correspond to a rumble strip depth, and y would correspond to a noise level, and we're indexing each of these observations. Nominally, we'll typically use a subscript I, for example. And so we can measure at site 1, there's a specific rumble strip depth and there's a specific noise level. Likewise, at site 2, 3, 4, so forth and so on, up to whatever our maximum sample size of n would be in this case, okay? And so what we're doing in least squares is we're trying to estimate those parameters, beta naught and beta 1, by minimizing the sum of the squares of the vertical deviations of each of these points from a best fit line. And so if we look at this graphically, let's say, as in our case here, we have a bunch of different rumble strip depths on the x-axis, we have some noise levels on the y-axis. We're basically trying to fit a line through those data such that those points are relatively evenly distributed above and below that line. And the way by which we're doing that is we're taking the distance between each of these individual points and that best fit line. We're squaring it, we're summing those differences, and then we're trying to minimize that respective quantity, basically, okay? Because there's an infinite number of different ways we could set up a line through these data points. And there's also an infinite number of ways we could do that, such that the points are relatively equidistant on both sides above and below that line. And so to make this tractable, what we're doing is essentially we're using that sum of squares quantity that we had introduced previously with our analysis of variance. And we're basically trying to minimize the square differences between the value we would expect to see at each level of x based on this regression model and then what we're actually observing, okay? And so if we think about those n observations in the sample, we can basically express them in this format. So the noise level at site I is going to be a function of the rumble strip depth, and we're going to also have some error, which is going to be unique to that observation. So in general, points are not going to fall exactly on this line, they'll fall above or below it. And the reasons for that may include some important unobserved factors that we're not able to capture in our analysis, or it just could be the underlying uncertainty and random and stochastic nature of those data ultimately, okay? And so as we think about trying to estimate a model for this and trying to determine what those parameters beta naught and beta 1 are, we're going to basically look at the sum of the squared deviations of those points from the true regression line, okay? And so what that means, in essence, we can think about this epsilon term as the level of error that's present within our empirical framework that we're investigating here, okay? So for each and every one of these data pairs, we can assume values for beta naught and beta 1, and we can determine how closely, based upon whatever given value we have of x, how close that value of y is corresponding to that value, and that difference is going to be captured by this error term epsilon, okay? So we're basically squaring that epsilon, summing it up across all n of our observations, and then we're ultimately trying to minimize that quantity, okay? And so that's what we see in the equation down here at the bottom. All we're doing here is we're simply rearranging this first equation such that it's in terms of epsilon, and so that error term then, of course, is just going to be equal to yi minus beta naught minus beta 1 x sub I. And so that quantity squared, and that is the function then that we're ultimately trying to minimize. And the way that we do that is as shown here. So basically just working through the algebra here, we're going to differentiate that equation with respect to beta naught and with respect to beta 1, okay? And we'll set each of those quantities equal to 0, and then through some algebra, and normally we'd go through a full derivation of this in class. I'll leave that as an outside exercise should you wish to work through that, but it's relatively straightforward. And then ultimately that yields what we see here, which are referred to as the least squares normal equations, okay? And so we can basically take this system of equations and we can basically isolate beta naught or beta 1 respectively, and that will give us the short form equations that are going to show up on the next slide here. And so those least squares estimates of the intercept and the slope are as shown here. So in the case of beta 1 hat, and so just quick nomenclature here, I may have introduced this previously, though I honestly don't recall. Anytime we have a parameter with a hat on it, it simply means that this is an estimate of the population parameter, okay? So we're estimating that population parameter based on our sample data. And the way that we're doing that is by using the equation you see right here. Now, it may not be obvious at first glance what's happening here, but we're basically taking each of our pairs of observations and we're taking the product. And so in our case, we're multiplying the depth times the corresponding noise levels. We're summing that quantity across our sample. And then we're subtracting off the sum of the x variable, which in this case would be the sum of the rumble strip depths across those 12 sites. We're summing up the noise levels at those same 12 sites, and then we're taking the product of those summations and we're averaging it across our sample of 12 observations. And then in the denominator, you'll notice the top and bottom here, the numerator and denominator are basically analogous. The only difference here is we're basically swapping in an additional xi for yi in the denominator. So hopefully that's evident from looking at this. And so we have our rumble strip depths squared, and then we're summing that across our 12 sites. And then be very careful when you're working through the calculations here that we're summing prior to squaring. So on the right side in the denominator, we're just summing our respective rumble strip depths and then squaring that sum quantity and then dividing by our sample size. And as you look at this, then hopefully it starts to make sense that this is basically, this is the slope. This is representing for any 1 unit change in x what the corresponding change in y would be. And so hopefully it makes sense just looking at the way this is structured, why we arrive at that result through this particular equation. We have alternate ways of presenting that that'll show up on the subsequent slide here. But when we go through an estimated linear regression model, in the simple linear regression case, our first task is to estimate what that slope term is, okay? Once we have the slope term, we can then set about estimating the intercept term. And so again, these are the same sample means we introduced previously. And so one unique aspect of simple linear regression models is that those models are always going to pass through the mean of our data set. So they'll always pass through X bar, Y bar. And so as a consequence of that, we can make use of that fact if we think back to the way our regression model was initially structured. So all we're doing here, we're taking our general relationship that yi is equal to beta naught plus beta 1 times xi. We're plugging in y bar for y sub I, we're plugging in x bar for x sub I, and then we're just rearranging this such that it's in terms of beta naught hat, which again is our estimate of that intercept term, okay? And since we've already estimated beta 1 hat and we can determine y bar and x bar based upon our sample, it's then straightforward for us to develop that estimate of the intercept term, okay? All right, and so the numerator and denominator of that equation, in some text, you'll also see those referred to as S sub xy and S sub xx. And so it may not be obvious just because we haven't looked at these equations in this form before, but you've definitely seen this equation previously in this class, and you haven't seen this, but it, as you can see here, again, they're essentially analogous equations. We're just swapping x and y between them. And so it may look a little bit more familiar now in this particular notation. So this is basically just an alternate way of calculating the difference between each of our individual observations. It's y value minus the mean of y times, sorry for that, my phone rang and everything has gone away. Okay. So I'm gonna just back it up. I'll have to edit that part out. My apologies. And so as we look at this quantity S sub xy, all we're doing here, we're taking each of our individual data points and we're taking the corresponding values of y, subtracting off the mean of y, times the corresponding value of x minus the mean of x, and then we're taking that product and summing that across our entire sample, okay? And as you can probably guess, the same thing is going to be true when we look at the equation here for S sub xx. And so obviously, or maybe not obviously at first glance, that's simply giving us our sum of squares for x, as we had introduced previously in ANOVA. So we're taking every individual data point, taking the difference from the mean, squaring that, and then summing it across our sample, okay? And then similarly, what we're doing over here, we're just taking the difference between each y value in the mean and each x value in the mean. And so consequently, you should be able to infer from this how this then results if we take the ratio of SXY over SXX. That's simply telling us for a 1 unit change in X, what corresponding difference we'd expect to see in Y as a consequence, okay? All right, now the easiest way to probably familiarize everyone with this concept is to just work through an example here. And so we're returning to the same data that was presented a few slides ago. We've got our 12 study sites. We have our milled rumble strip depth, our pavement type, and then our peak noise level, with the second column representing our X value, the fourth column representing our Y. And so we've already plotted these data out, and now if we wanted to go through and estimate our slope and intercept terms, we'd need then to calculate the corresponding quantities that appear in the preceding equations. So we need to figure out x bar, x times y, and x squared for each of these individual observations. And so first of all, summing up our x's, the sum of those depths across the 12 observations is 5.39. The sum of the noise levels is 971.6, and then dividing each of those quantities by 12 gives us our average rumble strip depth of 0.45 inches and our average noise level of 80.97 decibels, okay? Likewise, we're calculating x times y, and so of course that's relatively straightforward here. You see those quantities down this fourth column. Those sum up to 440.518, and then immediately after that we're calculating the quantities for x squared for each of the individual observations, and then as we had seen the need for in the preceding equations in the SXX term, we would also be interested in the sum of that corresponding quantity, okay? And so hopefully everybody's with me here. Now, from this point, it's a matter of us working through those least squared normal equations. And so again, we're given that our slope term is equal to the sum of the xi, yi column. And so we've calculated that quantity down here, 440.518. We're then subtracting off the product of the sums for x and y respectively. And so that would be 5.39 and 971.6. Again, our sample size here is 12. And then in the denominator, we've got the sum of our xi squareds. And so that's this quantity right here, 2.5751. And then lastly, the sum of our x's, which we'd previously identified as 5.39, that quantity squared divided by our sample size of 12. Okay. And so working through the math here, we'll find then that our slope in this case is 26.657 decibels. Okay. And so interpreted at face value, what that means in essence is that if we increase our rumble strip depth by 1 inch, we'd see a 26.7 decibel increase in noise levels roughly. So nearly a tripling of the noise level. Now, I should note here, we sometimes need to be careful when we're trying to interpret what these results mean from a practical sense. So in this context, we're never going to mill rumble strips that are 1 inch deep for various reasons, including impacts on pavement condition. And then incidental to that, the noise levels would also be quite large, presumably in that circumstance. And so in our specific case, we don't have that large of a range. Our min value is 0.25, our max value is 0.69. So we'd never actually see that level of variability. I'm just bringing that up in part because oftentimes we'll estimate regression models just using whatever the native format of those data are, whatever the native units when the data were collected. And so we just want to be careful that we're providing appropriate context. And so if we were writing up these results, for example, I would be reluctant to say that we'd see a 27 decibel increase in noise level for a 1 inch increase in rumble strip depth. And one of the reasons for that is we don't actually observe that large of a range of differences in our sample. And so this is a point we'll circle back subsequently to. But anytime we're trying to extrapolate outside the range of values in our sample, we should have some degree of concern about the reliability of those estimates. So what we'll tend to find, and we'll talk about this when we get into confidence intervals of linear regression models next time, is that the data tend to fit closest to the line when we're near to the mean value. And as our values, our x's and or our y's get extremely small or large relative to that mean value, they tend to diverge from that best fit line in most circumstances. Okay, so I started going on that long tangent in part because it's going to set up a very quick demonstration on the subsequent slides here. But in any case, we have our slope term, and since we have our slope, we can then go through and estimate our intercept as well. And so the intercept is just going to be equal to our mean noise level, which again, in this case is 80.97, minus the slope, which we had just estimated at 26.657 times our corresponding mean rumble strip depth of 0.45 inches. And so we work through those calculations and we'll find that our intercept in this case is 68.993 decibels. And so another brief tangent here for a second. What does that 68.993 quantity mean? Anybody in the audience? You should hopefully remember this to some degree, perhaps discussing this in prior statistics courses. So that's 68.99 decibels. What does that correspond to from a practical perspective, if we think about how this model is structured? Okay, so Nishal, thank you very much. So what that means essentially is that when our rumble strip depth is equal to 0, our noise level is equal to roughly 69 decibels. Okay, is that true? That's an open question to anyone. If our depth is 0, I mean, it basically means we have no rumble strips there. Any thoughts? Is that a fair extrapolation to make? Maybe, maybe not. I guess one way we could try to investigate that, if that was of interest to us. Yeah, great point, Farish. You got exactly where I was going with that. We did have the baseline noise level data from before. So we could basically estimate this equation, and what we could do, instead of including just these 12 measurements, we could basically double this and have 24 measurements, including the baseline noise when we're just driving off the rumble strips, and then secondly, our noise measurements when we're actually traveling on the rumble strips. And so we'll save that for a later time, but I guess without including those baseline noise levels at the onset here, it would be uncertain whether or not this would give us a reliable estimate. And that gets back to my preceding point with respect to the range of our values. So we're not actually seeing any noise levels that are this low, and we're not seeing any rumble strip depths that are near 0, frankly speaking. And so on the face, I wouldn't have a lot of confidence that this result has any meaningful interpretation. Okay. Now that'll vary if your data set actually ranges, all the way to 0, and if you have negative values are conceivable and things of that nature. There may be a meaningful natural interpretation there, but in this case, on a surface, that number seems like it might make sense, but we really don't have enough information in lieu of that baseline noise data to make a more definitive determination. Okay, and we'll circle back to that point again subsequently, but I just wanted to bring that up here. Now, back to one of the other points I had brought up in this discussion. I wanted to just quickly demonstrate what happens when we rescale either our X or Y variable. And so to my preceding point, what we've basically done here is we've previously estimated a regression model for noise levels as a function of the rumble strip depth in inches. Now, generally, when these depths are milled, they'll be milled at a depth of 3/8 plus or minus 1/8 of an inch. And so a natural question here is, well, what if we parameterize this model such that our depth, rather than being measured in inches, is measured in eighths of inches? And so as we think about that on the surface, does anybody have any thoughts? So if we're rescaling our X variable here, and we're thinking about our slope and intercept terms, are either of those going to change? Any thoughts? So we've rescaled our X variable, and now we're looking at noise level as a function of depth in eighths of inches. Would our slope change as a consequence of that? Any thoughts? Okay, you're all anxiously anticipating the next slide, I guess, at this point. So we'll just, okay, so Asan, great. So slope would be multiplied by 8 is his conjecture here. So that 26.8 or 9, whatever it was in the preceding slide, that would be 8 times larger? Or would it be 8 times smaller? And we'll find out in one slide. So here we go. So what we'll find here, all I've done, as I had alluded to previously, I've just rescaled our X variable here. So instead of 0.25 inches, we've got 2/8, and likewise all the way down for each of the other 12 measurements. Our Y variable is completely unchanged. And so as we look at our quantities of interest here, what you'll notice, since Y is unchanged, obviously the sum of Y is unchanged, Y bar is unchanged. And each of our remaining quantities has basically been rescaled here. So our prior value of X is now multiplied by 8. Our prior value of XY is now also 8 times larger. And then our value of X is 8 times larger. And so that's occurring twice over here. So 64 times the size for our xi squareds, okay? And so then as we work through the corresponding math here, what we'll find in the algebra, you'll notice that these numbers now are significantly larger. Anywhere there's an X, those are significantly larger. Our Y values are unchanged. And so interestingly, when we get to the last step here, we'll find that our slope is now equal to 3.3322, which is a rescale of our prior variable that was just beta 1 under our initial starting conditions divided by 8, okay? So the only thing that's happened here is that we've rescaled that slope term since the units on X are now different. And as a consequence of that, we're finding if we were to extrapolate that out and for a 1-inch difference, we just see 8 times that quantity. And so we've got the exact same relationship between X and Y, which should make sense intuitively. We won't want that underlying relationship to change, but that's simply been rescaled based upon our rescaling of the variables. What about the intercept term? Would the intercept term change? Any thoughts on that? Okay, we have a guess that not, and that guess is going to turn out to be correct here. So if we just work through the math here, obviously our Y bar is again unchanged. X bar has been rescaled. So again, this is now going to be 8 times larger. But as we just work through, our beta 1 is 8 times smaller. And so those effects basically cancel one another out. And at the end of the day, then our final calculated value for the intercept is the same 68.993 decibels we had seen previously. Okay. So important to note, I bring this up in part because oftentimes I've worked on research studies where we would get parameter estimates that are either incredibly large or incredibly small. And so it's difficult to try to interpret what those results mean or try to parlay that information to our audience in a manner that's meaningful. So if we talk about changes in decibel levels that are 3.3 decibels, that's probably reasonably easy for someone to interpret. Even in the preceding case, if we talked about 27 decibels, maybe. Now, if we multiplied this by a factor of 1,000 or divided by a factor of 1,000, we would get numbers that were very, very, very small or very, very, very large. And in those circumstances, that might not make sense. And so I bring that up in part because when we're presenting model results, you want to be somewhat careful about the units and the scales of your variable. And so in transportation, we'll often work with data that can be very large in nature. So things like the population of a city or county or state, or the number of vehicle miles traveled. And these numbers tend to be quite large. And so consequently, a 1-unit change in VMT is not going to give us, in a regression framework, a very meaningful slope term, for example. If we looked at the slope for changes in traffic volume on the order of 1 million VMT or 100 million VMT, we'd get much different numbers than if we looked at just per 1 VMT as an example, okay? And so that's just something to think about as you work through and start assembling your data set for the purposes of the course project, or even in some of the examples that we'll be working through in class here, okay? All right, so that gives you enough information to basically be dangerous here and work through and estimate a simple linear regression model. This is just showing a comparison between those two models we'd estimated previously. And as you'll notice here, they're basically indistinguishable from one another nearly. The only difference here is that we've simply had some rescaling occurring on the x-axis here, but the slope of the line, their general positions, is similar. It's just basically distorting that based upon the scaling of those respective axes. But the underlying relationship is going to be equally linear, I guess, as we'll say in each of those respective cases. Okay. Now, a natural question that arises from this point is, okay, it looks like there's a linear relationship between X and Y. but is that relationship statistically significant? Okay. And so there are several different ways that we can try to assess that hypothesis of interest. And within our context, we'll start by revisiting some of the analysis of variance concepts that we had talked about over the past couple of weeks, okay? And so ANOVA can also be used in the context of linear regression as basically just a general hypothesis test to determine whether or not there's a significant linear relationship between our two variables of interest, okay? And the way that we're going to make that determination is through our analysis of variance identity. And so you may recall when we worked through the ANOVA context, we took our total sum of squares and we partitioned it into its two component parts, right? We had the sum of the squares for the treatments, which was assessing the variability in the data and how much of that was attributable to differences between the individual group means and the overall means versus our error sum of squares, which was simply the difference between each of those individual data points within those groups and its corresponding group mean, right? And so in that setting, if we had very large differences between the group means and very small differences, relatively speaking, of the individual points within those groups, that would give us evidence of an effect, okay? And so we're going to use an analogous rationale here in the case of linear regression, except in this case, our total sum of squares is now going to be equal to our regression sum of squares. So SS sub R is regression sum of squares. We still have an error sum of squares term as we had seen previously. Okay, so in this case, we're taking that variability between each data point and the mean, that quantity squared, and we're partitioning it into two parts. So first of all, each of our individual observations is going to have a corresponding prediction associated with it, which corresponds to whatever the value on the best fit line is. That would be calculated if we plugged in whatever our value of xi was for this paired observation, okay? Okay. And so secondly, we're taking the distance between each of those individual predictions and then the mean of our data set. You'll notice there's not a subscript here because all of those data points have the exact same mean. And we've subscript each of the other cases because these are in fact going to be observation dependent, okay? And so in contrast to ANOVA, rather than looking at the relative differences between the group means versus the cluster of the points among their corresponding group means, in this case, we're assessing how much of the variability is due to the systemic difference between the mean value of our sample and that best fit line versus the error component here, which is just how far those points are distributed around that best fit line. It's probably easiest to think through this graphically, and we'll get to that in just a moment there, but this is just to basically reorient you in terms of how we would use ANOVA within the linear regression framework, okay? And so here we see that relationship, our linear regression model that we had estimated previously, and then we see our ANOVA identity. And so in trying to determine whether or not there's a significant linear relationship here, what we're basically trying to do is we're comparing the relative differences between the systemic effects, so the sum of squares for the regression, which again is just the squared difference between each of these data points. So for each value of X, you see the corresponding Y, and we're measuring the distance to this best fit line at each of those respective values of X, okay? And then we're squaring that difference. And that's our SSR, or regression sum of squares term, okay? Now the error sum of squares is simply the difference between each of these individual data points. So this is the vertical difference here, measured directly up or down to that line. We're taking these differences, squaring them, and summing them across the sample, okay? And so if you think about this in concept, what we would tend to find is that if we have a good fitting model and we have a linear relationship between our variables, what will tend to happen, the points will be clustered about this line. And so the differences around that line when we square them are going to be very small compared to the differences between this best fit line and the overall mean of the data set, okay? Because keep in mind, this total sum of squares that we're partitioning is just the square difference of each of these individual data points from the mean value in the sample, okay? And so in this case, you can probably tell before we even work through the ANOVA equations that we are going to likely see a linear relationship here. Now, in contrast, in cases where we wouldn't see a linear relationship, if you think about this conceptually, that would indicate that these points are scattered relatively far from this best fit line. And in the most extreme case, if there's no linear relationship whatsoever, they would just be randomly scattered at equal distances roughly around the mean here. And if we tried to fit a best fit line through those data points, that best fit line would basically just be flattened and be equal to whatever the mean value is, okay? And so in that circumstance, then, of course, we'd find that the difference between our predicted value and our mean value would just reduce down to 0. And all of our variability in that specific circumstance would be due just to random error, okay? And so that's one of the reasons why ANOVA is particularly important, because we can use it not just to compare group means, but we can use it across a number of other different settings as well. And there's a lot of intuitive appeal in terms of using that for hypothesis testing procedures, okay? And so if we think about this, the results from this analysis of variance can be presented in an ANOVA table, which is going to be very similar in nature to what you saw in the case of our test of means. The only difference in terms of the source of the variation here is that we're talking about SS for the regression instead of for the treatment. Calculation of these quantities are as they were shown on the preceding slide. And then our degrees of freedom here, I wanted to very quickly introduce some nomenclature here. So when we see P, P indicates a parameter. And so our model has two parameters. It has a slope term and it has an intercept term. And so for each of those parameters, we can think about those as though they're taking up an associated degree of freedom. Okay, so if we wanted to estimate a linear regression model, we'd need to have at least a certain number of data points in order to do so. And so our degrees of freedom for the regression are going to be equal to P minus 1. So in the simple linear regression case, we have 1 degree of freedom. We also, rather than P minus 1, we can also report that as K, where K is our number of regressors or predictor variables, okay? Now keep in mind here, our intercept term is not a slope term, it's not a regressor, it's not a predictor variable. It is a parameter in the model, but it's not telling us anything about that direct relationship between X and Y. And so that's why that's not included here. And so as we get to more complex multiple linear regression models, our degrees of freedom would be equal to the total number of parameters in those models minus 1, or the number of non-intercept regressors, okay? And from there, we always have n minus 1 total degrees of freedom for our sample if we think about how we would break up that total sum of squares into the sample variance by taking that ratio. And so our remaining degrees of freedom then are just simply equal to n minus p, or n minus k minus 1, okay? And so as in the case where we were comparing means, we're interested in ultimately calculating what our mean squares are. And so our mean square for the regression is just our sum of squares for the regression divided by p minus 1. And our mean squared error is just going to be equal to our sum of squares of the errors divided by n minus p, okay? And then the final step at the end of the day, we calculate the corresponding F statistic, which is just the ratio of the mean squared for the regression over the mean squared for the error. And in this context, we're again interested in only the one-sided test. We're only going to reject when values of F are particularly large here, okay? All right. And so this is just showing you, I've gone through, and for each of those XY pairs, I've used our predictive equation. And so this is telling us what Y hat is for each of those corresponding individual observations I. We also see our mean value here, which again is just 80.97 roughly. And so with X, Y, Y hat, and Y bar, we can then calculate our total, our regression, and our error sums of squares. And so first of all, our total sum of squares, so just taking each individual noise measurement, subtracting off the mean, squaring it, and then summing that, we get a quantity of 143.347. And so that's going to be equal to the the sum of our other two components when we try to partition that variability. So our regression sum of squares is just going to be equal to yi hat minus y bar. And so we're taking our predicted value minus our mean value, squaring that quantity, summing that. You can tell here that quantity is relatively large relative to our SST, so 109.497. And then lastly, we're taking the values of each individual data point compared to how well it fits to that best fit line. And so these differences are generally tending to be relatively small. And so summing those across our sample, we get an error sum of squares of 33.847. Okay. And so calculation, very similar to what we had done in the ANOVA case where we're comparing group means. And just carrying that data over to our ANOVA summary table. We have our regression sum of squares. We've already talked through our corresponding degrees of freedom there are just going to be p minus 1 or k, which in the simple linear regression case is always going to be 1. And that leaves us with 10 additional degrees of freedom for error, and that would be our sample size of 12 minus our number of parameters, which is 2 in this case. And so consequently, 1 degree of freedom for the regression sum of squares, 10 degrees of freedom for the error sum of squares, and the mean squares are just the ratios of those quantities. And so our regression sum of squares is, again, the mean squared error is just 109.497. Since we've got 10 degrees of freedom, our mean squared error is 3.385. And then our F statistic is going to be 32.35. We would compare that to our critical F value. Now, keep in mind, we'd be using nominally the 0.05 significance level table. And keep in mind, to use the F table, we need to consider our numerator degree of freedom, which is 1 in this case, and our denominator degrees of freedom, which is 10. And so we'll find out at 0.05 with 1 numerator and 10 denominator degrees of freedom, our critical value is 4.96. We're well beyond that and far out into the tail, and we'll see that our corresponding p-value in this case is going to be 0.0002. So this is going to be highly significant at 99.9% confidence, essentially. And so based on that, we would reject our null hypothesis. And apologies, I'm remiss. I guess I had not included that in the preceding slide, but when we go through these hypothesis tests, and I think we'll return to this on a subsequent slide, our null hypothesis is basically that that slope term is equal to 0. And we're trying to assess whether or not that slope is non-zero. If the slope is non-zero, that means that there is in fact a relationship between X and Y. Okay. All right. A few other nuances. So one thing we're often interested in is determining the variability of our actual regression estimate. So if we looked at our yi hats, our prediction, it would be interesting to us to know how variable that is. And so interestingly, the variance of the regression equation is just simply equal to whatever the mean squared error is. And so in this case, we just take each individual observation, take its difference from the predicted value from the regression equation, square that quantity. That's our sum of squares for the error. We divide that by the corresponding degrees of freedom. And then that in turn will give us our estimate of the variance for the regression equation. Okay. Now, what we'll often do and what you'll see as output to standard statistical software as an analogy here. So you can use ANOVA to conduct our significance for the test of the slope, but we can also use t-tests, okay? And we can use t-tests for both the intercept and the slope terms. And so here you'll just see what the corresponding estimates or equations are to derive those t-statistics. And so as we've seen in any of our statistical tests up to this point, we're generally looking at some parameter of interest divided by its corresponding standard deviation, okay? And so in this case, we estimate our slope term as was shown previously. We divide by our estimate of sigma hat squared. So this is our mean squared error term. And then the degree to which that varies is as indicated here. So we're multiplying that quantity times 1 over n plus x bar squared over sxx, okay? And consequently then what we're going to find, so this is just telling us if we take repeated samples from a population, where we have a known relationship between X and Y. There's going to be variability across that sample, and that variability is going to depend upon several factors, including the sample size. And so as our sample gets larger and larger, as we've seen in prior cases, that variability here will tend to be reduced in larger samples. We'd be more likely to reject the null hypothesis. And likewise here, this is just basically giving us a sense of the relative variability in our X's. And so depending upon whether it's more or less variable, if we see greater variability in our X, that's going to basically give us greater uncertainty and greater variability in our test statistics here. And so that's what's being accounted for in the denominator here. Now, generally speaking, you're not going to be asked to manually calculate this. This will be developed as output from a statistical analysis software program, though we will, for the purposes of the homework assignment, give you at least one round of practice in going through and manually conducting these t-tests, okay? Now, likewise, in evaluating the slope, as we've seen previously, in this case, our numerator, again, is just going to be our estimate of that slope, beta 1 hat. Our denominator is going to be the square root of our MSE term, so that variance estimator divided by SXX, okay? And so in essence, what we're seeing here is as that SXX term gets very large, this quantity tends to get very small, and then in that circumstance, we'd be more likely to reject the null hypothesis, okay? And so we'll quickly work through on the next few slides these respective test statistics. And so in the case of our initial problem testing for the intercept parameter, our intercept was 68.993. Our mean squared error was 3.385. And so again, that was just our 33.85 SSE divided by 10, which was the corresponding degrees of freedom. Our sample size was 1/12. Our mean value was 0.449. We're squaring that quantity and then dividing by SXX, which is 0.154. And so our test statistic is going to be equal to 31.71. And our degrees of freedom with any of these corresponding tests are going to be N minus P, which in our case, again, we had a sample size of 12, 2 parameters. And so we'd look at our critical T statistic with 10 degrees of freedom. Obviously, a statistic that this is this large is going to lead to us rejecting that null hypothesis regardless of what the sample size is. And then for the case of the intercept term, our slope of 26.657 is divided by the square root of, again, our MSE divided by SXX, 5.68. And so again, in both of these cases, we're going to find that we reject the null. And in this case, that means that there is a significant linear relationship between X and Y. And in the case of our intercept term, it basically means we have a non-zero intercept. We have confidence that our intercept is also non-zero, okay? And so real quick, as we look at those tests of regression and whether we're using ANOVA or we're using the t-test procedures, it's important to know this is assessing whether or not there's a linear relationship between X and Y, not just whether there's a relationship, period. Because what we see right here, these are two different instances where we don't have sufficient evidence to reject the null. Now, in the first case, in figure A here, it's pretty evident there doesn't appear to be any sort of relationship between X and Y in this case, right? Now, in the latter case, in contrast, there very clearly is a relationship, but it looks like that relationship's of a higher order. And so if we tried to fit a linear regression model through those data, we wouldn't be able to. We'd basically end up with just the mean of the data back as a result. But that would probably misrepresent or distort our view of that underlying relationship. And so there are ways that we can try to accommodate this type of relationship through linear regression, and we'll talk about that a little bit more next week. But I wanted to raise that point. And then relatedly, the next slide shows examples of cases where we do find that there's a significant linear relationship and we can reject the null that beta 1 is equal to 0. However, in this case, it looks like we're capturing what in fact is a nice, clean linear relationship Whereas in this case, and this is similar to what you saw in the preceding slide, in this instance, the relationship would reject the notion that there's no linear relationship, but it looks like linear is essentially a misspecification, or we're not able to estimate a model that's sufficiently sophisticated such that we can capture the true relationship between X and Y, okay? And so just a quick note, so the t-test and the ANOVA will give us useful information, but there is some additional diagnostics we should think through, and that largely gets back to my initial comment about you plotting the data before you get started in any of these respective analyses, okay? And so I think that is, okay, this is our last slide, I believe, for today. Another related concern is goodness of fit. And so the way that this is traditionally assessed in the context of linear regression is via R-squared, which is our coefficient of determination. And loosely speaking, what R-squared is telling us is the proportion of the variation in our Y variable or a dependent variable that is explained by the value of the independent variable, okay? And so, for example, if R-squared was equal to 1, it would mean 100% of that variation in Y is explained by X. It probably also means you have a problem, because it would be very unusual that you'd see an R-squared of 1, but smaller values of R-squared would indicate that we're explaining lesser amount of that variability, and then larger values of R-squared would be indicative of us explaining more of the variability. Now, with that being said, I should note that R-squared is really only useful to us when we're comparing competing models on the same data set. And so in this case, we could have estimated a model rather than based on rumble strip depth. We could have based it on the baseline noise level we talked about last time, or we could have estimated a model based upon pavement surface type or various other factors. And so in those cases, we could compare those R-squareds to one another, and we could say with reasonable certainty the models that have larger R-squareds are better from a predictive or explainability and inference standpoint, okay? That's not the case if you're comparing models on different data sets. So if we're trying to predict how many crashes would occur on a rural 2-lane highway, we might have an R-squared of 0.1, for example. And if we're trying to estimate or develop a predictive model for the amount of travel that occurs on a daily basis, let's say across counties or across states or some very high level of aggregation, I guess with the caveat, exclusive of COVID, because COVID has introduced some changes. But generally speaking, those models would have very high R-squareds because those numbers tend to be very stable over time. And so we'll return to this fact later, but I just wanted to introduce some caution, because oftentimes, even in technical research papers I review, people will talk about having a quote unquote good R-squared. And so you've got to be a little bit careful with that, because that's only a useful metric for comparing models on the same data sets ultimately, okay? And so to calculate R-squared, as the definition up here implies, it's telling us what proportion of that total variability is explained by our dependent variable. And so frankly speaking, that's just the ratio of our regression sum of squares divided by our total sum of squares, right? So SST is capturing the total sum of squared deviations of each point from the mean, and SSR is telling us how much of that variability is being captured by that best fit regression line, okay? An alternate way of calculating R-squared using the same ANOVA relationship we'd introduced previously is simply 1 minus our error sum of squares, which is just the variability of those points around the best fit line divided by our total sum of squares, okay? And so in our specific case for this data set, our regression sum of squares was 109.5 roughly divided by 143.3, or 1 minus 33.8 over that same denominator. And so in this case, we have an R-squared of 0.764. There are some tests we can use to determine whether or not that coefficient of determination is significantly different from 0, but those test results are going to give us the same result we saw from our test of the slopes or our general ANOVA test there. And we'll circle back to that one subsequently. But in any case, R squared in this case, I guess I'm comfortable saying that we have a relatively good fitting model despite the caveat I just introduced her, but it does appear that the rumble strip depth is doing a good job of helping us to explain or predict what levels of noise we'd expect to see at those respective sites. Okay. All right, so with that, I think we're done for today. We've got about 12 minutes or so left, it looks like here. I didn't know if anyone has questions on anything from today's lecture or respect to the literature review or the assignment. Again, the lit review is due on Friday. The next assignment is due a week from Friday. And again, I'll get feedback to everyone on those over the next day or two. And in the meantime, we'll start getting into the Mannering book, and that will tend to become a lot more useful to you. A lot of the things we've covered over the front portion of the course have been more general in nature. So with that, thanks everyone for the time. And if there are any questions, I will hang around. Otherwise, I think we're good to go. Thank you. No questions? Everyone's
Dr. S, I have a question related to the literature review. So, is it supposed to be like expanded literature review, or like the one that we write for paper, like 1 or 1.5 pages, like a concise one?
good question. Yeah. I'm not expecting a comprehensive literature review. So as an example, we have a lit review we did for a speed limit study that was, oh gosh, I don't know, somewhere between 60 and 100 pages in length as an example. And in this case, I'm looking more for a lit review as you would see in a term paper. So in terms of length, I would say no more than 3 pages. So somewhere between 1 and 3 pages, with 2 being kind of a sweet spot there. And as an example, I would just point you, if you look at most research articles, they'll generally follow that same structure. The only exception is occasionally you'll see review articles. So as an example, Dr. Gates and I had just authored a paper, or actually an encyclopedia chapter that focused on a specific topic. And so that ended up being, I don't know, 10 to 15 pages in length. And in our context, the primary purpose of this lit review is to capture all of the most important and most recent literature that relates to your topic, to give the reader some context as to what your contribution is. And so subsequently, as a result of that, I'm looking for the shorter version, I guess, based on your question. Does that make sense?
Yep. Thank you.
Okay. Any other questions on anything course related? Oh, real quick question, I guess, and I guess you can just show hands and thumbs as the case may be. How many of you have data sets in hand at this point? Okay, so it looks like we've got quite a few hands going up. We'll start checking in on that item next week. I just want to make sure once we get clear of the term paper, or not the term paper, once we get clear of the midterm exam, the term paper will play an increasingly large focus, and we'll start to use a lot of this in-class time even to try to assist everyone with working through the term paper stuff. But I would strongly encourage you to at least start trying to track down any data that you're intending to use for analysis purposes, because depending upon the topic area, in some of those instances, there might be a bit of front-end effort trying to go through and conduct a review of the data and identify any data quality issues that you need to address. In other cases, your data may be more or less ready to go, but there'll probably be some variability from project to project. But okay. Any other questions from anybody?
Dr. Saulani, when will you think we can have your feedbacks on the introduction section?
So my plan is to get those out to everyone today. I'm just checking my calendar real quick. I've got a meeting at 10 a.m. and then I've got a couple hour gap, and I'm going to try to get the lit review, or sorry, the introduction reviews out by that point. And so I'm going through and I'm reviewing the Word and or PDF documents, and I'm annotating those, and then I'll post those back to D2L with just some general notes. So you should expect to have that later today. Okay.
Yeah, thank you.
Yep. All right. Okay. If there's no other questions, then you are all free to go. I'm going to hang around for quasi office hours. There's a few students that want to chat about a few things, but otherwise, I will see you all next Monday. Keep in mind, you'll be here by yourself. Well, presumably by yourself. I won't be here on Wednesday morning, given the mini spring break. So enjoy all that entails.